It's now my pleasure to introduce tonight's speakers. We have three, which is very unusual. The first of them, in no particular order, I'm told, is Parney Albright. Parney has worked on national security since 1986. He served as director of the Lawrence Livermore National Laboratory, LLNL, and as president of the Civitas Group. He was assistant secretary for science and technology at the Department of Homeland Security and served concurrently as both assistant director for Homeland and National Security in the White House Office of Science and Technology Policy and senior director for research and development in the Office of Homeland Security. He also has worked at DARPA and the Institute for Defense Analysis. Notably, he led the formation of the Science and Technology Enterprise at the Department of Homeland Security during its formative stages. He earned a BS in Physics and Applied Mathematics from George Washington University and a PhD in Physics from the University of Maryland, and I'm told he is a local boy, so to speak. John Edwards is Associate Director of the National Ignition Facility at LLNL, where he also serves as Director for Inertial Confinement, Fusion, and High Energy Density Structure. He leads the Inertial Confinement Fusion Program and is responsible for directing the X-ray drive ignition effort, about which we will be hearing tonight. Previously, he was the group leader for high energy research and alternative concepts at the United Kingdom Atomic Weapons Establishment. He's a fellow of the American Physical Society, and he is an author on over 100 journal publications. He earned a Bachelor of Science in Physics and Astrophysics from the University of Birmingham in the United Kingdom and a PhD from Imperial College London. And our third speaker is Omar Hurricane. Omar is distinguished member of the technical staff at LLNL, where he is lead scientist for the high-foot implosion campaign at the National Ignition Facility. His research is focused primarily on high-energy density physics science, plasma instability, and weapons physics. He is the recipient of DOE's Ernest O. Lawrence Award for National Security and Nonproliferation, a number of DOE Defense Programs Recognition of Excellence Awards, and several LLNL Director Science and Technology Awards. He is an author on more than 60 journal publications. He earned a BS in Physics and Applied Mathematics from Metropolitan State University of Denver and an MS and the PhD from UCLA. Their talk tonight is entitled Exceeding Fusion Fuel, Break-Even with Lasers at the National Ignition Facility. Parney will give a relatively short introduction, and then Omar, and then, I may have this backwards, but Omar and then John, and then Omar will present the main part of the lecture. So, Parney.
So first of all, thank you very much for asking us to talk about some of these, I think, very exciting results here today. It's actually gotten quite a bit of press around the country, so you're in a position now to talk to the people who actually made that happen. I'm in a bit of an uncomfortable situation here as being the person who is sort of the setup man for the people who really did the work on this. I think it's mainly because I have the grayest hair of the bunch. But so I'm going to spend a little bit of time talking about the National Ignition Facility as a whole, and then turn it over to the people who are really going to talk about the topic of today's topic. So what is the National Ignition Facility? The National Ignition Facility is, and you're going to hear a little bit more later on about the details, the mechanics of how this actually works, but it is by several orders of magnitude the largest laser facility on the planet. It occupies an area of several football fields. For any of you who come out to the Bay Area, I would encourage you to take the 30-mile drive out to Livermore and take a tour of the facility. It is one of the most impressive engineering accomplishments on the planet. It produces 1.8 megajoules of energy. and 500 terawatts of power. It is, by the way, just as a side point, for those of you who saw the movie Star Trek Edge of Darkness, is that what it's called, right? Almost every scene that was in the engine room of the Enterprise was actually filmed out at NIF. It was the set that they used. They came and took over the place for about 4 weeks while we had a maintenance stand down, and one of my most treasured photographs is me with J.J. Abrams. It occupies a place of honor for me. Someone had asked earlier at dinner how much the facility costs. It costs about $2 billion to build, and its annual budget is sort of on average around $350 million a year to do the experimental work at the facility. So why was this thing built? It actually was built with several missions in mind. The most important mission, and the reason that it is funded by the National Nuclear Security Administration, the people who make nuclear weapons, is to enable something called stockpile stewardship. And what stockpile stewardship is really all about is how do we sustain both how do we sustain our nuclear weapons stockpile, and very importantly, how do we sustain the workforce that is a very important part of the deterrent when we no longer are doing nuclear testing. The last time this country did a nuclear test was in 1992. And we haven't built a new weapon since. And so these weapons age with time, and there are also things we want to do to the weapons in order to make them more safe or to make them more secure. And as you make those changes, you have to have very, very smart people who understand the implications of those changes in order to make sure that the deterrent remains a deterrent. The facility also has as its mission other national security applications. It performs experiments periodically for the non-proliferation community. We're not going to talk much about those, in fact, at all about those this evening. It enables frontier science, and the reason for that is, as I said in the prior chart, that NIF samples regions of temperature and physics, temperatures and densities and material science that only exist in a laboratory setting, that only exist at the center of stars, in the middle of gas giant planets, and also, it turns out, in the middle of an operating nuclear weapon. That's why it was built. And then finally, if you can, there's a portion of the experimental program at NIF that actually deals very much with how nuclear weapons operate. I'm going to say a little bit more about that in a moment. But it turns out that the kinds of experiments that you do are identical to the kinds of experiments you would want to do if you were trying to do inertially confined fusion energy. And so that's what you're going to hear a little bit about this afternoon, about those experiments. They were done primarily in support of the nuclear weapons program, but they also have a parallel role in terms of exploring the possibility of an essentially limitless source of energy. So, as I said, it provides some very critical experimental data for stockpile stewardship without the need for underground tests. If you ever, I don't know if they still give tours out at the Nevada test site. I think they do. If you ever go out there, it's actually a fairly spare place. But what you see is a lot of dimples in the ground, and that was from the hundreds of underground nuclear tests this country conducted from the 1960s through 1992. And the idea behind NIF is to obviate the need to ever again have to do that. So let me say a few words about how a weapon operates, because it'll help, I think, maybe provide some context for the kinds of experiments that were being done, and why it's also so important to do these experiments if you want to explore the possibility of inertially confined fusion energy. So the way a weapon operates is, for those of you who don't know, there are generally two components to a weapon. This was called the primary and what's called the secondary. The primary is a fission weapon, and its whole sole purpose is to drive what's called the secondary, to provide energy to cause the secondary to explode to very high yield, right? So if you think about the weapons the weapon that was built that was exploded over Nagasaki, that was a primary only weapon, okay? And Hiroshima was a primary only weapon, but for this country since the 1950s has had two-stage weapons. And so the idea behind, so the way the primary operates is it's generally it's a hollow sphere of plutonium, and there's a chemical explosive wrapped around it. It explodes, it compresses, and as it compresses, it reaches critical mass, and you start to get a nuclear fission reaction, the same kind of reaction you would get in a nuclear reactor, except now it's going supercritical. What that does is it heats up some gas that we have injected into the middle of this hollow cavity, deuterium tritium, and the fission reaction that's occurring around the primary causes that deuterium tritium reaction it gets up to about 1,000,000 degrees Kelvin, and it causes fusion reactions to occur. Okay, it just gets that hot. Those fusion reactions create a lot more neutrons, and the purpose of those neutrons is to complete the fission process that was started by the chemical reaction, and thereby drive the secondary. So one of the key uncertainties associated with how a nuclear weapon operates are the details. I mean, what I just said is very easy to say, at least it's easy for me to say. The details of the physics of it are actually very, very complex. And the idea behind NIF, one of the things that NIF is designed to do is explore how that fusion reaction occurs in a compressed hot deuterium tritium plasma. Then once that's happened, you would then have to transfer the energy from the primary to the secondary, and then you go to the secondary and you get another implosion that occurs that provides a lot more yield. Very important. So the point here is that NIF is really designed, in fact, it is a unique capability within the United States to sample all three of those phases. In fact, the other major uncertainty that this country had was in the energy transfer part of this. It actually was by far the largest uncertainty we had in our understanding of the physics of nuclear weapons. And actually, Omar, the reason he won the Lawrence Award was because he was actually the person who, in partnership with the NIF facility, solved that problem. So this is, again, these are the set of experiments that we conduct at NIF. And the one I described at the outset of this business about DT burn, is really one of the things it does. It does many, many other things. Okay? Again, all associated with the fact that it can uniquely sample temperatures, densities, and material properties that occur inside a nuclear weapon. So we are doing all of these things, but one of the things that I'm not sure I can get this thing to work, but one of the things that we don't do, that we have so far not succeeded in doing, is getting to what's called ignition. One of the key aspects of NIF, and one of the reasons it was built, was to explore this process called ignition. We have yet to succeed at getting ignition. And how is ignition defined? Ignition is defined by getting more energy out of the fusion reaction than the amount of energy that was put in. So it's defined as getting more energy out of the process through the fusion than the total amount of energy that was put in, including the energy that was put into the laser in the first place. So that is how ignition is defined. So we've been going through a very long process for trying to approach what is an extraordinarily difficult problem to do in a laboratory setting. And what you're going to hear about today these are a lot of terms, but basically the kinds of experiments we are doing are what are called integrated experiments, and then more focused experiments that are designed to move us down the path toward ignition. And we hit a little while ago a pretty important milestone, which I guess you're going to hear more about from John. So with that, I'll turn it over.
Well, thank you, Parney. How's the sound? Good at the back? Great. So someone is interesting. Actually, Parney already thanked our host. I'd like to thank them again. This is a wonderful opportunity to come and tell you about some of the really, we at least find incredibly exciting work that's going on at the Lawrence Livermore Laboratory. Someone asked me at dinner, they said, well, of course, you work in a nuclear weapons complex, so how do you know? Do you have guidelines on what you can say about weapons? And you know, and I now know, from what Parney said, exactly what we're allowed to say about nuclear weapons. So here's the Lawrence Livermore National Laboratory, and what you're going to hear from us is you're going to hear something which is really about an engineering marvel at the first instance. This is the National Ignition Facility itself. To get ignition, which is in itself a scientific grand challenge, we need to have unprecedented control over our positioning systems and our temporal control systems. So this is the sort of story that you're going to hear from us. So here's the Lawrence Livermore Laboratory. It's about 1 mile square. Here we go. It looks directly out over to, from this view, over to San Francisco. And the NIF laser is right over here, and that's what we're going to be talking about. What I'm going to show you now is the laser in operation. So there's a little movie that we have, and I'm just going to let you watch it. I'll comment as we go through.
Shot director, ready for shot.
So this is the control room. They're just about
Ready
to start
countdown
off.
for shot on my mark. 3, 2, 1, mark. Clock is running. 5, 4, 3, 2, 1, shot.
So those are large capacitor banks for all the energy stored. They energize amplifiers. In the meantime, the laser pulse itself is created in the master oscillator room here. It's fed through fibers. It has about 1 nanojoule. It gets amplified through that process by about 1 billion times. And it's going up and down through amplifiers, and it's going through special filters. And that's the light pulse. It's a finite length in space. It's 20 billionths of a second long, 20 nanoseconds. And this process is getting amplified by about another 1 million times. This in here. The beams are square. There's 192 of them. It goes through the various amplifiers, and now it's going to go off towards the target chamber. They play this music every time they have a shot. So now it goes through this elaborate labyrinth of mirrors, and it does that because they all have to arrive at the target at precisely the same time. And they arrive there in about, I'll tell you in a minute. Right now it's red, the color of the light is red, it gets converted to blue light, and it does that because the target right in the middle of the chamber, it doesn't like red light, but it likes blue light. So there's the target we call a whole round, and we'll explain a bit more what that is in a minute. It's actually made of gold, it's about 1 centimeter, ½ inch long. The lasers come in, heat up the interior, it gets so hot it creates X-rays. The X-rays start to heat the capsule, so much so that the material ablates off. And in a rocket reaction, it gets imploded inwards. And if we do it properly, with exactly the right timing, that's what will happen. And the energy that you get out is would be about 20 megajoules or so. What's 20 megajoules? 20 megajoules is about the same energy content as about 1 kilo or a couple of pounds of coal. So let's just go through what's got us so interested right now. What's got us so interested right now is the laser, as Parney said, it delivers about 1.8 megajoules to the system. And that goes into that thing we call the whole round. And some of it gets lost. There's always losses on the way. One of the things we have to fight. So you get about 70% of that gets converted into these X-rays. A much smaller fraction, only about 10% of that actually gets into the capsule itself. A lot of that goes up into the X-rays, actually heat the wall of the whole round and heat the interior. And the capsule's a small piece in the middle, so only a part of it gets heated. Part of the X-rays get absorbed. And then finally, the fuel itself, which is actually inside the capsule, has less than about 1%. So there's this large energy cascade. We only get about 1% into the fuel itself, which is about 12 kilojoules. And the numbers will become more significant a little later. So what's the big deal right now? Well, the big deal is that. And it doesn't look particularly big, but what's exciting for us is for the first time in the laboratory, we've actually got more energy out of this of the fuel than we put into it. So that's not ignition yet. So you can see ignition, as Parney was saying, the ignition is making this, the size of this guy, the size of that guy. Okay, so if we blow that up, what we've actually done, and these are the experiments that Omar has actually been designing, he's been our lead designer on this, in a very nice, carefully sequenced set of experiments, which have been going for over a year now, we've got about double the energy out of the fuel than we put into it. And there's a key process here that we're going to talk about in a minute that is absolutely central to getting to ignition. We're starting to see that process now. So that's what's got us excited. Now let's step back and talk about fusion a little bit more. Well, to get fusion, you need some extreme, what I've called here a machine. Nature just does majestically at this. This is our sun, and it's an extremely hot ball of plasma, and it's confined by gravity. It's very massive. It's very old, 4.5 billion years old, and it's pretty stable, as we know. We're sort of here today. And at the center of the sun, the pressure at the center of the sun, and this is the key thing, it's about 250 billion atmospheres. And essentially it's there forever. Now, what we try and do on Earth is we try and recreate these plasmas. Now, one idea which was born back in the 50s is it's called magnetic confinement. So what we do here is we have a plasma, like the sun, and it sits inside what we call a tokamak in here in this ring, and we use magnetic fields to confine it. But it's right at the other end of the spectrum. It's atmospheric sort of pressures, and the idea is it's confined for seconds. And this machine here, this is something called ITER, and the central coil here, that's about 13 meters high. So this is a massive machine. And the idea behind this machine is it will demonstrate fusion energy at by the magnetic confinement method, and it's some ways off right now. It's being built. But that's the idea. What we are doing is this. It's called inertial confinement, and it came about in around 1970 or so in this form. It was actually John Knuckles who dreamt this up, was thinking about it before then. What's significant and totally coincidental is that the pressure that you generate inside this target here, it's about the same as the pressure at the center of the sun. So we're trying to create conditions that are absolutely extreme, very similar to the center of the sun, but they don't last for very long. They last for a fraction of a billionth of a second. So this was the paper. This was John Knuckles way back. He looks somewhat different today, but this is the paper they published in Nature, and it was all about compression of material to super high densities. And the story you're going to hear today is it's all about compression, and that's why we need that precise, very precise control over our directionality and our time. That's John a couple of years ago, just as enthusiastic. We're 50 years on from this, and he's just as enthusiastic today in wishing us to get there as he was back when he thought of this idea. So what is fusion? Well, fusion is, in this particular instance, where we take deuterium and tritium, the two isotopes of hydrogen, and these two isotopes, they like to fuse. And I sort of have to qualify what I mean by like. When I say they like to fuse, they sort of like to fuse by about a factor of 100 more than any other thing in the universe. And that's significant. So that's sort of the first miracle that you need to happen here. But they're positively charged. Right? So when you try and get them together to make them to fuse, they want to push each other apart. So the trick is you have to get them up to like 50 million Kelvin, 50 million degrees. So that's what I mean by easy. Now, what happens is that these guys fuse together and they produce a helium nucleus and a neutron. Now, the neutron, that's the thing that the fusion energy guys are really interested in. The neutron doesn't interact much with anything. It flies out, and they capture it, and it heats up material, and that's how you generate steam and your power. What we are interested in is we are interested in this helium nucleus. That thing doesn't go very far, and that's what's critical to making ignition work. And let me explain what I mean by that. So imagine here we have our alpha particle, and we have some deuterium plasma. And what we're trying to do is we're trying to deposit energy, the alpha particle energy, in this deuterium-tritium plasma. And that's the critical thing. What happens is that if you trap the energy, it heats itself up even more, the reaction rate goes up more, you create more alphas, you heat it up more, and it's a bootstrap reaction, and it will, what we call ignite. So that's what the whole ignition thing is about. A critical parameter there is not just the temperature, but something we call rho r. And rho is just the density of the material, the mass divided by the volume, and r is the size. And if you have enough of that, what will happen is the particle will stop. If you don't have enough, it will just go straight through. All the energy goes out, and that's not good enough. So you have to have high rho r. And there's ways you can do this. You can increase the rho, okay, or you could change the r as well. But you put more particles in here, then the alpha particle will collide and it'll stop. And that's the key. The other way you can do it is you can take the same number of particles you have there and compress it. And that's key to getting ignition on the NIF, and you'll see why in a minute. So that's this idea, same number of particles, compress it up, the rho R goes up. So what rho R do you need? You need a rho R of about 1. Now rho R has that function, also has another function, which is why we call it inertial fusion. It's just like the mass of the system, and if you push on something that's more massive, it takes longer for it to disassemble. So the more rho R you have, the more mass you have, the longer it takes to disassemble, the longer you have to heat it up. Okay, so that's another critical piece. But you need a rho R about the size of a baseball, it turns out. And it's about half the weight. Now, to heat that up to the temperatures you need to get it to the 50 million degrees, to get it to actually burn and ignite, takes a lot of energy. And as you heat it up, of course, it wants to cool down, so you have to do it really quickly. It would take about the same amount of energy that an average US household uses in a year to heat that up to the temperature that you need. If you were able to do that, just suppose you were able to do that somehow, we don't know how to do it. Yeah, what would that look like? Well, it would kind of be pretty interesting. It would give you, there are various ways you could show this, but this is about 5 kilotons. So I could have put a mushroom cloud, I could put anything there. You know, that's not particularly useful to anyone. Well, not for these sort of purposes anyway. So that doesn't look very attractive. So remember, what I said was you just need rho R. Now, if we keep the same rho R, if I compress that, what happens is the rho R goes up. So if I keep compressing, I can start throwing material away. I just need this rho R, this particular value of rho R. So I keep compressing and compressing, I can throw more and more material away. That means the amount of material I have left is less, the energy I need to heat it up is less, and the amount I will produce is less. But the amplification here is clearly large. The amplification there, the energy is also, to heat that baseball up is also equivalent to about 20 pounds of TNT. But if it burns, you're going to get 5 kilotons. So what do we do on NIF? Let's just jump straight to what NIF tries to do. So it requires very extreme compression. It requires compression from solid density DT, which is about 1/4 of a gram per cc, to about 1,000 grams per cc. So several hundred times the density of lead. And to get it to heat up enough, we create something called a hotspot in the middle, which is sort of the match or the spark. This is where all the nuclear reactions start and the alpha particles start whizzing around. And this is where it lights. And then once it's lit, once it ignites, it starts to burn into the rest of this fuel and it burns up the rest of it. And if we make this work, as I said, we'll get something out which is about equivalent to 1 kilogram the energy of coal. And the amount of mass that we've used here is really small, very, very small. The amplification is over 1 million here relative to something like coal. So where are we? Well, we're about halfway there. There are a number of different ways to look at this, but we can create conditions which are perhaps a little bit more than this now, but about halfway there. The extra factor of 2 is quite challenging. And you'll see why, especially as Omar starts to go through the details of how we have to do this. And it really is technically rather challenging. All right, so this is a story about, as I said, compression and precision in time and in space. So here's the National Ignition Facility. The target area is at this end, and if we take the lid off, you can see what we saw in the movie. So these are the capacitor banks here and here. The main laser amplifiers, this large slabs of glass, which we'll show you in a minute. There's about 400 megajoules of energy stored in here, and we end up with 12 kilojoules into the fuel at the end there. If you look in here in these laser amplifiers, you take a view down there, that's actually what it looks like. And you can see some people here working on it, so you get an idea of the scale. All of the glass amplifiers are in here. These are filters which make the beam very, very smooth. The glass itself in there's so much glass in this thing, they had to develop special techniques and they roll it. And then they chop it up and they polish it. And once they polished it, there are these very, very smooth surfaces. And it's that color because there's a special material in it called neodymium. And it's that all the flash lamp energy, when we energize them, that neodymium absorbs all the light. And that's how we get all the energy out of into the laser beams themselves. That was the target chamber. It's enormous, about 10 meters across. It had to be lifted into the facility. That was back in 1999. And there it is today. It's surrounded. There's actually a floor here, which you can't see. It's been taken out. But what you can see is this is where all the beams come in. The target chamber, it's got a big wall of concrete on it to stop the neutrons from doing too much damage, and various diagnostics around there. These are what we call the final optics assemblies. So the light comes in here and it gets converted from red light into blue light. Now, the story behind a lot of the technology in NIF is absolutely remarkable. The story behind the optics themselves, the intensity of the light that runs through the final optics is 10 joules per centimeter squared. That probably doesn't mean anything to you. Most optical things will be blown apart at about a joule. So the development that went into the NIF glass was quite remarkable. This is pushed way beyond anything that anyone else can do on the planet. And they're working on actually making that even better. And it's all to do with how clean the surfaces is, imperfections. It's just a remarkable science all in itself. So moving into the center of the target chamber, that's one of the positioners. This thing itself, it's huge. It's actually about 10 meters long, and it's got to stay stable to about the width of a human hair, about a quarter of the width of a human hair. It's remarkable. The whole facility is on its own foundation. It's isolated from the rest of the world, basically. And even then, when trucks go by, you can actually see this thing move around. It's really quite something else. That is the target. Now, the target's an engineering marvel. This thing has to be cooled down. The first smart thing we do, I talked about compression. Hydrogen and helium is just gas stuff. So the first smart thing we do is we freeze it. Okay, we get a factor of 10,000 right there, pretty much. So that's the first smart thing we do. And the target itself is frozen. And you're going to see some nice pictures of that when Omar gets up in a minute. But here it is. There are, I can't go into all of this, but inside there's this hologram. It's made of gold. Some of them are made of uranium. There are things that we can look through to look at the capsule in there, which Omar will talk about. We have to put these arms here, they cool the target down to about minus 290 degrees or so. So about 17 Kelvin. That's when the hydrogen will freeze. And to make it spherical in there, we have to put, sounds silly, we have to put heaters on there. And we put heaters on either end so that we can control how uniform the ice is inside this target. It's absolutely remarkable. And they have to be controlled to within about a millikelvin. And this whole thing is about 1 centimeter long. So there it is. To keep it at 17 Kelvin, you have to take some special precautions. It's sort of hard to keep something that cold. So we put these shrouds on there. They're very special shrouds. They fit around the target here. This is how it keeps cold. We call it cold finger. This is a very, very cold temperature. There are shields to shield just the ambient light. That would destroy the layer completely. A huge amount of technology went into just making this work. Of course, then we fire the laser and we destroy this beautiful target. And it's about the energy of a hand grenade going off. And it sort of wipes everything out. So, but then, we have to, how do we get on to doing ignition experiments? And that's where I'd like to introduce Omar. And he can tell you exactly what we have to do to prepare now. So I've got you all the way to the target now with the laser, and Omar's going to take you inside the target and tell you what we do there.
So before we actually do the DT implosion, I am going to try to impress upon you, actually, you don't just start putting those targets into the laser facility and firing them off, because if you did that, you'd have a disaster. As John tried to tell you, that there's a lot of precise control that's required to achieve these large levels of compression. So we actually do a number of preparatory experiments before doing a DT implosion, and I've outlined them here. We do something called a re-emit that looks at the radiation pattern on the surface of the capsule. We want to try to get that as smooth as possible. We have a precisely timed series of shocks that we need to input into the capsule through the laser pulse. And to diagnose what shock timing we have, we do these experiments called keyholes that give a little streak of a Visar laser image telling us what the velocity versus time is of these shock waves entering the capsule. We do experiments called SimCaps, which tell us the shape of the hot spot. That's the spark at the middle of these implosions. We want to get that as round as possible to make as most efficient use of the energy that we put in as possible. And these experiments tell us what we have to do to find round. This one is a little pancaked, and that one is a little sausaged. So that tells us we need to do something in between. We do a set of experiments that we call 2D Con-As, which means convergent ablator is our term. And they tell us the shape of the the plastic rocket that's driving the implosion in, that's absorbing the X-rays and driving the fuel itself. And again, we're looking for something that's very round and with as few imperfections on the surface as possible, and sometimes things don't work out that way, and that gives us clues about some things that we might need to fix. We do another set of convergent ablator experiments that are called 1D Kanes that basically tell us as a function of time and diameter where the shell is, when it hits the middle, and how thick the shell is as a function of time. We use that to get the velocity and remaining mass of the ablator. And only then, after doing these preparatory experiments, do we start doing DT implosions. So I'm going to just reinforce these ideas about compression because it's really important, and also kind of tell you what the trick is. The trick for ICF is to just turn about 100 million atmospheres of pressure into about 300 billion atmospheres of pressure. So as you've already seen, our Hall-Rom target here, which is about 1 centimeter long, it gets blasted by these lasers that convert to a bath of X-rays on the inside of that metal shell. And again, it's about 1.8 megajoules of energy. The conversion process of the laser to X-rays loses energy, about 500 kilojoules. And it's that bath of X-rays that then causes the surface of the capsule to explode. Because the capsule has a small surface area, relatively speaking, compared to the inside of the Hall-Rom, you don't absorb all that X-ray energy. You only absorb about 150 kilojoules of it. So you can see that's roughly a loss of a factor of 10 right there. But in absorbing that X-ray energy and exploding the outside of that capsule, in this case it's plastic, the pressure generated is about 100 million atmospheres. And that high pressure on the outside of the capsule drives it inwards, again like a spherical rocket. The rocket accelerates the fuel, which is inside that little capsule, to high velocities, generally about 370 kilometers per second is what we're shooting for. We've actually attained that now. And that kinetic energy that was delivered to the fuel is about 14 kilojoules. So again, we lose another factor of 10 in energy, which is unfortunate, but that's the way it is. And we're trying to then slam all that kinetic energy into this final little bit of the implosion, forming a hot spot with a cold fuel layer around it, and trying to achieve about 300 billion atmospheres of pressure. And as John told you, we are at about 180 billion atmospheres only so far. So that's still a respectable pressure. Why try to get that very high pressure? Well, and the reason is there's a very simple scaling that tells you how the energy required for ignition scales with stagnation pressure. And the higher you can get the stagnation pressure, the less energy you need to achieve ignition. And this is why we haven't done it in the laboratory yet, because with laboratory levels of energy, you have to get these pressures enormously high. If you have a lot of energy available, like they did in the 1950s, if you're using a fission explosive, you don't need nearly as much finesse to get this to work. So the implosion actually is a pressure amplifier. That's just the nature of implosions. You trade away energy to get pressure. That's just the way they work. Here's a picture of the capsule. I'm going to blow that up for you so you can actually see what goes into it. Here's the assembly. We have a plastic ablator here which absorbs those X-rays. Again, it's about 2 millimeters in diameter at the center of that Hall-Rom. The experiments that I'm going to tell you about use plastic, CH, carbon, hydrogen. We are looking at other materials as well, and each material has its pros and cons. There's a layer of silicon dopants that are about 2% in mass fraction that are buried inside the surface. That's this dark band. And that actually protects the inside of the capsule from high energy X-rays that would try to stream in and start to heat up. What's shown here, it's just this ghostly image of the cold fuel. So on the inside of this capsule, there's a whole team of experts, by the way, that do this. We've frozen onto the inside of the capsule this about 70 micron thick, or about 0.1 millimeter thick layer of DT fuel that's going to go on for this ride as this shell implodes. The outside of the shell looks shiny. In fact, it's not. The surface finish here is about 100 nanometers. It's manufactured to high tolerance, but if you look close enough, it does have imperfections on it. There's a great team down at a laboratory called General Atomics in La Jolla, California, which is a great place for surfing too, that make these capsules to these very high precisions. It's quite beautiful. We're looking for something that's as smooth as possible on the outside. but also as round as possible, because again, if these capsules aren't round, we don't make efficient use of the energy, and things don't work as well as we want. And again, the through thickness of that plastic is about 195 microns, which is about 2 human hairs. When we compress this with the X-rays that come out of the Hall ROM, we squeeze it down to a tiny spot. It's about 35 times in compression. That spot, again, is another human hair in diameter. So when John told you that, well, if things work perfectly, we get about, a kilogram of energy out, a kilogram of coal's worth of energy out, keep in mind it's coming out of a spot, the diameter of a human hair, and it's coming out in a time of 1/7 of 1/1000th of a second. And so, maybe that's a little more respectable than you might first assume. Here's how it works if everything is working. This is an actual simulation of the coupled Hall ROM capsule system. It kind of shows you what we're trying to achieve, but also illustrates what some of the pathologies are, and I'm going to tell you about some of the terms here that I might slip into using. We have the holes at the end of the Hall ROM that allows the laser energy to enter. We generally call that the LEH, laser entrance hole. The Hall ROM itself is filled with helium gas. The reason why there's helium gas in there, you can see as the lasers hit the gold wall of the Hall ROM, it tends to create a plasma and blows in. By putting in helium gas, we can hold back that gold wall, which gives us a better chance of getting the laser energy into where we want. Otherwise, the gold would stream in and get in the way of the laser energy. It also holds back the ablator, which is now, you see it here exploding in response to the bath of X-rays, generating those high pressures which drive the implosion inwards. So this is all designed. You choose the density of the helium gas, the position of where the laser beams hit the Hall ROM, all to try to control the shape of the implosion and get the timing of the implosion that we want. The laser energy enters the Hall ROM as a function of laser power versus time. A characteristic laser pulse shape is shown here. A little blip of energy at the beginning, another blip, and then a rise to peak power at the end. That's kind of how it should be working. But for a long time, things weren't working. And this plot here is just a bar chart, so it should be very simple, but it actually tells a pretty interesting story. It tells you where we've been and where we are. So this bar chart, basically I'm plotting here fusion yield. This is essentially time. The way we label time at the facility is by shot number. The shots here are labeled, the first 2 digits are the year, the second 2 digits are the month, and the third 2 digits are the day. So this is several years ago. You might have heard of the National Ignition Campaign. That's what several years of effort were spent on trying to get these implosions to work. It wasn't just getting these implosions to work, it was building up all those other experiments and the diagnostics as well. But again, the goal was to get implosions that were giving interesting results. But things weren't working for quite a while. Basically, 1 year in, the pattern was clear to a lot of us that things weren't working as expected, and something probably should be changed, but it just so happened things didn't change, and kept trying to make these things work, and it just wasn't working out. The reason why, again, in hindsight, these probably weren't working out is kind of very analogous to if you ever seen a young man step up to the plate at the baseball game. And the young man, a very strong young man, just wants to hit the ball out of the park. And he takes a swing at the baseball, and of course, usually what happens is you miss completely. That's usually what happens when you try for the home run. And that, not to be too mean, but that's what was happening here. Trying to go for the most extreme implosion that would give the most attractive fusion gain led to a lot of whiffs, a lot of missing the ball. So the strategy that we applied to make progress was actually to step back from that. Don't try to go for the home run. Instead, try to go for a base hit or even steal a base if you can, just to start scoring some points. And that's the philosophy we applied with the high foot. We changed something to try to make the implosion more controllable, less fickle, but we made a sacrifice in doing that. These implosions, which are showing very high yield compared to what came before, will never get as far as these could, in theory, get to, but did not get to in practice. The other thing that's illustrated on this plot, aside from fusion yield versus time, is a breakdown of how that yield is being delivered to us. The blue shows how much yield is coming out from the implosion due to the compression that we've put into it. And more or less, for more or less the history of fusion research, that's all that we've gotten back out. But the pink is actually now showing the amount of energy we're getting from this feedback process of alpha particles in the fusion reaction, leaving energy behind and feeding back on itself. And you could see at this point we have more than a doubling of energy due to that self-heating, or what we say is a bootstrapping process, where the fusion reaction starts to help itself. The other key point that's illustrated on this slide is the energy balance, as John mentioned in his presentation. The black line shows the energy that's been delivered to the fuel. We actually infer that energy delivered to the fuel by measurements made of the implosions. So it's not actually a computer model that's used. We actually can infer what the energy is just by looking at all our diagnostics of the implosions. And you can see this again kind of represents the history of fusion research, always getting out less than you put in. But you can see in August, or actually September of 2013, we've actually transitioned to a point where we're starting to get out more energy from the fuel than was put into the fuel, and we've continued to push that upwards. And so that's one of the things we're excited about. Of course, we want to push that even further. Okay, so what is this high foot thing that I'm referring to and that John referred to? Basically, it's kind of a funny trick. We didn't change the targets. We're using the same targets that were used before, the same capsules that were used before. All we've done is we've modified the pulse shape that we asked the laser to deliver. And the modification is more or less illustrated here. We ask for a little more power at the beginning. Actually, it's about twice as much power at the beginning. We drop out of the old pulse shape this feature here, which launches a shock. And we shorten the pulse shape so that it's about 5 nanoseconds, 5 billionths of a second shorter in time. But more or less, this shape here shown in black is essentially the same shape shown here. What this does is actually reduces hydrodynamic instability, and I'll show you what that means in a moment. We also trade off some things by doing this. We actually end up putting more entropy into our implosion than we'd like. That fights against compression. The way we measure that entropy is this term we call adiabat. We actually increase that. We'd rather not do that, but we wanted something to work, so we made that sacrifice. There are other characteristics of the implosion that we gave up on. In-flight aspect ratio, actually that's better for stability to reduce in-flight aspect ratio. It's basically a measure of how far you're throwing the shell compared to the thickness of the shell. And then the convergence, basically convergence is compression. We gave up on some compression to get this thing to work, and it's quantified by that number. But again, the main reason was control of instabilities. So in a cartoon way, what we felt was going on before with the implosion was something like this. Instead of being nice and round and smooth, it was tearing itself apart. And by transitioning to this high foot pulse shape, we could quiet that down and exert better control. In terms of actual, simulation and theory, this is the set of calculations that we based our assertions on, and what we felt was happening with the old implosion and would happen with the new implosion. So what this shows is this shell of the ablator at a certain radius, about 200 microns in radius. You have to remember it starts off at about 1 millimeter, so it's flown in about 4 times its radius. This is about the time at where the implosion reaches peak velocity. This is an axis of symmetry here, so spin this thing kind of this way, and you can kind of get an idea of what the full implosion looks like. What we felt was happening with the low foot NIC implosion, it was starting to rip itself to pieces as the implosion proceeded, and by the time you try to achieve the state of highest compression, it's turned itself inside out, and that means failure. By applying this high foot technique, we could quiet down those instabilities, and the higher we raise the foot, the more we could quiet that down, and the more intact the implosion would be at its final stagnation. This is about 50 microns in radius, about 100 microns in diameter. So again, this is about the diameter of a human hair. And what we're looking for is a controlled center and an intact shell around it. You can also see here the sacrifice that we made. John emphasized a lot, we need to get high densities, high compressions. That's illustrated by the color scale here, and that's what the old implosion was trying to achieve, these very high levels of compression. We gave up on that, as shown here in green. We get a lot less compression, but we now have control. So it's a trade-off. So I want to show you, in addition to the assertions that we made that led to the campaign of implosions, we also did do a set of detailed experiments that tested our assertions explicitly. And I want to show you one because it's going to show you how diabolical these instabilities are. This is an experiment where we take one of our implosion capsules, we cut a hole in it, we put this cone in, and we basically do like a dental x-ray of the surface as a function of time. We put on the surface controlled perturbation, so we know what the surface quality is like. And what we're looking for is bands of light and dark that tell us how much the surface has deformed as instabilities grow. And what I mean by that is shown here. So this is going to be a little movie of this particular experiment. If you look at this, here's the plastic shell, which is our ablator. Here's our cone, which we're looking through. And if you look at this, this shell looks perfectly smooth. But this also illustrates how diabolical instabilities can be and why they're so dangerous for implosions. The top part of this plot is density, by the way, and the bottom part is radiation temperature. So you'll see the bottom get hot and the surface explode. And for a long while, it looks pretty smooth, and it's flying inwards. Of course, in the real implosions, we don't have this gold cone sticking in, but we're trying to diagnose how the instabilities grow. But then at peak velocity, you can see the shell start to bust apart into all these pieces. In this case, it was because we put on a controlled perturbation, so it's a very regular looking structure. In the actual implosions, we don't want to put on those perturbations, but again, nothing can be made perfectly. And eventually, we can diagnose this in these experiments and test the veracity of our claims. And also, by the way, because half the team are designers and use simulation tools, we need to test the veracity of the simulations to make sure that we're not misled by them. So the experiment serves two purposes. So I'm going to show you here what our actual high-foot implosions look like. This is a side view of the implosion as it's fusing. This is a top view. You're looking top down on it as the yield is being produced. And you'll see, even though I've been stressing we're trying to make things round, well, it's close enough. No, no, it's not as round as we'd like. So this is one of the things that we've had to deal with, but it's the reality is in trying to make these things work, it doesn't always come out perfectly. The side view here shows the implosion is somewhat pancaked. So imagine taking a sphere and squeezing it on the poles so it looks a little squat. And if you look at it from the top, it actually has a nice toroidal shape, which is great actually if you're in the magnetic fusion area because you're always trying to make a tokamak. And so it has an interesting donut shape as well. So we've had to deal with this with many of our implosions. And it's been a matter of learning and testing things to try to eliminate that. And we're actually making progress in that regime. This shows the side view and top view of our best implosion using a gold Hallraum. And again, the scale here, this is 100 microns, this is 0, this is minus 100 microns. And so again, 100 microns is about the diameter of a human hair. This is the top view. This one is not quite as donut-shaped as the one I was showing you the movie of a moment ago, but it still is a donut shape. If you take the side view and the top view, you can reconstruct the actual shape. And in this case, it looks like a plum to me. We've had other pieces of fruit in our implosions, apples and other things like that you can identify. What we've done recently, and this was just back in January, is we've changed the Hallraum material from gold to uranium. And by changing the Hallraum material from gold to uranium, you can see we've actually gotten better control of our shape. The side view now is a little more round, And the top view doesn't have this donut shape anymore. Now it's more like a cracker. It's not perfectly round still, so we're still dealing with that. By changing the shape, though, and changing the shape only, this particular set of experiments was designed as a pair where it had exactly the same implosion time and exactly the same what we call bang time when the yield is produced, the same velocity of the implosion. We found a factor of 1.5 increase in yield going from this to this. So just changing the shape gave us a significant improvement in the implosion quality, and you can see in the reconstruction it's a lot more round. Here's a summary, not quite like the bar chart, but it's still a summary of all the shots we've done to date. This shows the trade-off that we've made and the performance gains that we've had. The blue dots are basically that two or so years of low foot implosions under the NIC, where there was a struggle to try to get the yields up, which is this direction up on the plot. You can see these low foot implosions basically sit to the right of this graph, and that's kind of in the regime where you have higher ρr, higher degrees of compression. If you go to the left of the graph, you have lower degrees of compression, roughly about half from here to here. And that's where our first high foot experiments took place. Our first high foot experiments were okay, kind of in the vicinity of the other low foot experiments in terms of yield. You can see the trade-off, though we made things less compressible. But because we had more control in the implosion and had more control over these instabilities, we were actually able to improve performance by turning up the laser energy. And that's these sets of shots here. So by turning up the laser energy, we were able to recover some of the compression. Because we're throwing this faster, we can actually squeeze it up harder and have control of it and get higher yields. And recently, we've passed this boundary of becoming alpha heating dominated, where the fusion reaction is actually helping itself by leaving energy behind and heating itself more, and so on and on and on. Ignition is up here, however, so we need to keep climbing up these contours of yield multiplication to get to where we want to go. And to do that, basically, there's a very simple way that you would approach this problem, and it has to do with mountain climbing. And a lot of research actually follows this metaphor. So if you want to climb Mount Everest, actually, and people have and tried for a long time, the first attempts to get to the top of Mount Everest led to failure and actually disaster. There was a first, second, and third attempt, never got quite to the top of the mountain. And actually, not all the people made it back. But that didn't mean actually that you couldn't climb Mount Everest. Other teams came back and tried to get to the top, and they took what was called a base camp approach, where instead of having one team trying to get up to the pinnacle, you'd actually have several base camps, and each base camp was trying to find the best path to the top of the mountain. So what they would do is they'd set up their base camp partway up the mountain, and they'd strike out in different directions, try to find the best path to the top. And the best path to the top would depend on the weather conditions and the local terrain. And by working together, eventually, people were able to climb to the top of Mount Everest. So we're essentially implementing the same approach with what we're doing. We're starting with an implosion now where we stepped back from the home run, but we have control over it. And by stepping back, actually, we took a leap forward. It actually works pretty darn well and has achieved something significant. But we want to go higher. So the mountain we want to climb isn't to the top of Mount Everest. It's actually the stagnation pressure that we want to get up, the stagnation pressure at the center of the implosion. But, you know, because our knowledge is imperfect, we have to try many different things. So we have many different base camps that we're attempting to climb up this mountain of stagnation pressure. And they're more or less outlined here. We need to get the velocity up in our implosion. And one strategy for doing that is to use thinner ablators, basically pushing the same pushing less mass with the same force gives you higher velocities, higher accelerations. We want to further improve our hotspot shape control. I've just shown you an example of how to do that. We changed hull rum materials, but there are other things you can do with the hull rum, like changing the geometry and so forth. We want to actually make the fuel more compressible. So this is one of the sacrifices we've made. We actually put entropy into the fuel by using this high foot implosion. We need to take some of that entropy out, so we're going to look at further pulse shape modifications. You've already seen by just making what looks like a modest pulse shape modification, we got drastically different behavior in the implosion. That was only the one other try, so let's look at there's a whole infinity of different pulse shape modifications we can attempt, so we need to research those. And then finally, there's other ablator materials, and each ablator material has its pros and cons in terms of the performance of the implosion. So what we've done through this body of research, we've kind of identified key issues, but we've also achieved significant gains. In particular, the self-heating and the fuel energy gain, or a fuel break-even, if you want to use that term. We've identified instability in mix as a major factor, and we've kind of gotten control of that. We still are wrestling with implosion shape, but we're making progress, as I just showed you. We want to get the implosion speeds up and try to compress the DT more, because it's, again, all about compression. But in the process of studying this and doing this, we have produced more fusion energy output from the DT than we put into the DT. But this, you still need to be careful. This is still a lot less than what came out of the laser. And we're getting these yield multiplications of more than a factor of 2 from this feedback self-heating mechanism. And this plot here basically shows the energy breakdown going on in these implosions. This is time going off to the right. What we're getting right now is in the hot spot, which is the center of the implosion, these alphas are kind of wrapping back in and leaving energy behind, which further amplifies the fusion energy coming out of the hot spot. We want to get more of that. And eventually, when that hot spot gets hot enough, we'll be able to burn the cold fuel around it, and that's when we'll liberate very large amounts of energy. And so that's where we're headed in the future. So with that, I think that's the end of the evening. So
Do you want to field the questions?
I don't know. I will only field technical questions. All political questions go to them.
We have time for a few questions.
Do you do this, or do?
We will have microphones going around the room.
Okay.
And please stand up when you get the microphone, state your name, tell us if you are a member or a guest, and ask a question. Don't make a speech.
Hi, my name's Isaac Schomer. I'm a guest. My day job is a patent examiner. And my question is, have you tried for the fuel using either platinum or palladium with deuterium and tritium adsorbed?
No, actually, we have a problem. For us, if you put in high Z materials, materials basically any higher up the periodic table than plastic, they tend to radiate energy away very quickly. And so that's basically the problem with mix. We need to keep things have atomic number close to 1. Otherwise, the radiation, the X-ray radiation, which goes as the atomic number squared, will carry away all the heat that we try to put in, and the implosion would not work. So, yeah.
Stuart Reuter, Navy League. I may be the only person here who's actually touched a nuclear weapon. But my question is more engineering and less physics. After you blow the thing apart, how long does it take to get the debris out of the chamber?
Oh, how do you do it? You know, it's actually all turned into a gas, so it's vaporized, basically. It's all vaporized. Our shot cycle, though, is about, you want to answer that, John? Or?
Yeah, so the debris that comes off, the total mass of the target, I can't remember the total mass now, maybe I can remember. But actually, it's got so much energy, it blows off, and it would coat the optics on the outside of the chamber.
That's what I was concerned about.
Yeah, so what happens is we have these, what we call debris shields. And we now have, and it used to be that we'd have to go and change them, and we now have disposable debris shields. And they're pieces of glass which go in. They have to be very smooth themselves, and this debris gradually collects on the optics. And after a while, after it collects enough, it stops the laser light coming through enough, and you have to replace them. We have to control the energy, all of those beams to a very high precision, 192 of them. And so we have to have a model for how the debris builds up on the debris shield. We have to account for that. So it's mind-boggling how these guys do it, but they do. And there's a big cassette there with about 10 of these things in, and when it has enough, they change them out. And that's where all the material goes.
Thank you.
Got a couple up here.
No,
My turn is next. I've got the mic.
Oh, okay, good.
Your name and whether you're a member or guest?
Yes, my name is Edith Weeks, and no, I'm not a member. I'm just visiting this evening, and thank you for your presentation. Your presentation was reminiscent of a NASA presentation to me. I'm a professor of outer space development, and so my question for you, what I was sitting here wondering the whole time is, NASA always has to justify why this research is necessary. So my question is twofold. One, is your research that, what was it, $2 or $3 billion to start up the project, and then there's an annual budget? Is that taxpayer funded? And then two, there didn't seem to be any justification at the end as to why this research is necessary or how it's going to benefit the public or who it's going to benefit.
Okay, let me take that on. Yeah, I'll take that on. Yes, this is 100% taxpayer funded, 100%. And it is all of the funds for all the things that we've been talking about tonight come from the National Nuclear Security Administration. And the point to much of what we're talking about here, there's the rationale for it, which is a good rationale, is to try to have a much better scientific understanding under controlled laboratory conditions of what happens inside an exploding nuclear weapon. Now, you could argue about and so it's part of our overall national security posture. You know, most recently reaffirmed in President Obama's nuclear policy review that was published, what, a couple years ago, I guess it was, right? Where these kinds of experiments were in particular called out. And I will tell you, one of the greatest supporters we have of this program is Senator Feinstein, Zoe Lofgren from California, you know, a large number of people who see the value of these kinds of experiments so that in order to prevent us from ever having any reason to go back to doing nuclear testing. And then secondly, it's because of, I think, the potential many people see for this kind of research should it go forward. And you know, there are huge daunting engineering problems attached to whether or not this could ever become a viable source of commercial energy. And there's enormous engineering issues associated with it. But nevertheless, once you've shown you can do it, then it sort of creates, you know, a certain amount of impetus to go see how, you know, to try to make that work as well.
Thank you.
My name is Scott Matthews. I have a question that I think might be related to the first question, and that is there any thought about putting other elements not on the outside of the capsule, but on the inside of the capsule with the cold fuel, essentially doping the cold fuel? Even though the DT fusion is the easiest one to drive, could some other high Z mixed in there help you recycle more of the alpha energy or even maybe some of the neutrons?
So we did look at actually coating the inside of capsules with high Z material like tungsten. We did actually experiments at a sister facility to NIF called Omega, which was in Rochester, New York. Theoretically, if instabilities and mix didn't occur, you would get something that we call radiation trapping. And a high Z material, just like the way the hull realm works, it's a metal can that we shoot the lasers into to keep the radiation in and get things hot. Well, you could put another metal can inside the implosion to try to do the same thing, and that radiation trapping could help you if it didn't tear itself apart. But what we found in those experiments, it tends to tear itself apart. So that didn't seem like a viable path, but we did look at something like that. And there's still, you know, there are a lot of ideas, and it's a matter of kind of triaging the ideas. There are logistical reasons. Sometimes they're hard to fabricate, so we want to try easy things first and so forth. But eventually we'll get more ideas covered, certainly.
Any other questions? John? No, go ahead. You have, I didn't see you have.
I'm Bob Terry. I'm a member of the society, and I had a sort of a two-part question. The limiting factor on the energy coming out of these implosions is really how much symmetry you can get. And in your weapons program, you're trying to assert that you can use codes to predict what comes out of these implosions, yet your simulations are two-dimensional, and to mimic what goes on in a weapon, it's got to be three-dimensional, and three-dimensional radiation transport hydrodynamics can probably stagnate any computer we can build. So how is it that you have great confidence that you'll be able to predict the material, properties of something that's a 3D radiation hydrodynamics event? On the other hand, in energy, if I look at the energy return on investment from one of these things, the energy return on investment is how much energy I get out versus how much energy I put into the system to break the energy loose. Most fuels that I deal with have energy returns on investment 10 or 20 or 30. This system right now appears to have an energy return on investment, maybe I'm wrong, but it seems to be 10 to the minus 5. And so, in fact, cold fusion is probably more competitive than this fusion as an energy source right now.
Could you ask a question?
And so, so my question is, with this kind of a large hill to climb, where do you see the leverage to really close the gap 5 orders of magnitude?
Yeah. So actually, let me answer the second question first. And I'm going to answer it with a metaphor. And so imagine a stick of dynamite that's got a fuse on it. And you light the match, and you start making comments that, well, there's not a lot of energy coming out of that match. And then the fuse starts burning, and then you say, well, there's not a lot of energy coming out of that fuse. But remember, it's connected to a stick of dynamite. And once that fuse burns to that stick of dynamite, there will be a big change in the opinion of how much energy is coming out. And so that's essentially what we're trying to do here. We are assembling a stick of fusion dynamite. We are tickling the fuse. And it is a tiny amount of energy right now with a not so respectable return on energy investment. But if we can get that fuse to burn to our stick of dynamite, that is when things change. And so that's what we're trying to achieve. Also, as John said, once, or it was Parney that said it, once you show something can work, the ideas will start pouring in on how to do it smarter, more efficiently. I think a lot of technologies work that way, and I think history shows that. So we'll just have to see. I'm not going to promise anything to you about whether or not this will actually ever be a practical energy source. Right now it has this purpose that's national security. It is useful for bouncing designers against who never witnessed or were involved with nuclear weapons development and our codes. And so that brings me to this first question that you had. And I have to be careful. I don't like the guys in black coats showing up with sunglasses and dragging us out. So I have to be careful what we say. So we do three-dimensional simulations now. It's not a matter of practice because they tend to take a long time. We do two-dimensional simulations quite a lot, and a lot of our technical underpinning is based on those. But that is exactly why it's important to do experiments. And it was, you have to test the veracity of those computer models to the best that you are able, and the veracity of the people who use those models to make national security decisions or inform people who make national security decisions. It's not perfect. We're not going to get everything, but it's better than not doing it at all. And that's where divergences from reality can really take place if you never touch base with reality and just believe theory and models. So that's my answer to that. I don't know if you guys want to add anything.
I'll just add one more comment, and that is the process that Omar just described, coupling very high-performance computing, and I will tell you that the biggest computers in the world are being developed at the nuclear weapons laboratories. And that's just a statement of fact. We have a 20 petaflop system at the lab right now, which I think is, depending on how you score it, number 1 or number 2, something like that. But I would also argue that we actually know a lot more about how nuclear weapons work, the science of it, than we knew back from the day when we were when we were blowing these things up in the desert and creating those dimples that I showed before. I mean, in a lot of ways, the nuclear weapons test is it's not a very controlled experiment, and there's a lot of the thing that NIF gives you is a lot of control. You can vary lots of parameters, and you can test your theories and regimes in ways that the nuclear weapons test doesn't allow you to do. So you learn, so nuclear weapons science has moved largely away from what was kind of a semi-empirical approach, much more toward a theoretical approach where when we build approximations into the computer codes, we have a much better understanding of what the basis is for those approximations, and then we can do experiments to test that.
John Ingersoll, I'm a member of the Society. Follow up on the previous question, the laser component seems to be a huge factor of 100 loss of energy.
Yeah.
Do you foresee any way to bridge that gap? Because no matter what you do with the whole round, you still have a huge deficit.
I will comment a little bit on that, but I'll maybe ask John to comment. Go ahead. I'm sorry.
Second question, when you use the gold or the uranium coating on the whole round, is that to increase the radiation gain, the heating of the target, or what is the purpose of gold?
Okay. Let me try to answer both of those, and okay. So yes, it's a large laser facility. It took a long time to build. Okay, as a result of that, it was using technology having to do with lasers that is more than a decade old, maybe 20 years old. And as with all technologies, it's improved since then. I believe, and John could maybe correct me if I'm wrong, you can get a factor of 10 back with current laser technology. So this is the old technology, much like the space shuttle, used technology from the 1970s to build the spaceship for the 1980s. It wasn't the technology that we have sitting in front of us right now, but there's no way it could be because these large infrastructure projects just take too long to build, and you have to use known technology at the time for the design. I don't know if it will get any better than that, but I'm sure people are going to try.
What kind of laser do you use in the improvement factor of 10? Is it a different laser or the engineering?
It's about diode laser, yeah. Yeah, that's not my expertise, so diode lasers. So your second question, the gold hole room. Yeah, so uranium versus gold. So basically...
why use gold or uranium? Is to increase the heating of the...
Yeah, so essentially you're trying to stop radiation from leaving.
Right.
And the higher you are up on the periodic table in terms of atomic number, the more effective materials are at stopping radiation from leaving. So gold is pretty high up on the periodic table, and that's why we use it as a matter of practice. If you shot lasers at something lower down on the periodic table, the energy would escape too rapidly. Uranium is even higher up on the periodic table, so it's even more effective at stopping the radiation. So it's really just a matter of atomic number and the number of electrons around your atom, because those intercept the photons, and the more of those you have, the more effective you are at stopping photons. So.
We're going to have...
Yeah, people don't like plutonium, I know. Uranium, okay, it's an actinide, but it's actually not that bad. And so, but plutonium, you'd rather not. So people are sensitive about that. You could make it thicker, but the problem with making it thicker is, yes, you stop the radiation from leaving, but you're now putting radiation into the thickness. So the radiation is lost to you either way. You've just heated up a larger mass of material. So that's why making it thicker by itself doesn't help.
We're a little pressed for time, so we're going to have one more question in the back.
You can get me after drinks.
You're going to have more questions.
Zeynep Dilla, I'm a member of the society. In another life, I thought I was going to be a laser scientist. So your entire infrastructure, the beam shaping, the, what was it, 196?
192, yeah.
Megajoule and 500 terawatt laser. It's too impressive for words. I just have a couple of questions about the laser technology there. One is converting from red to blue. It is from
it's
which wavelength to which wavelength, and what technology do you use? ODP or?
It's frequency doubling, but John's more of an expert on that.
It goes from 1 micron. It goes from 1 micron to 1/3 of a micron, and we put it through KDP crystals. So it converts to green, doubles, and then the double and the primary mix together to get the third harmonic.
I see.
And and you know, that's another, I've forgotten about the history of that. You know, these crystals they're huge. And we had to grow, well, there's 192 beams, and I'm not sure we grew 192 crystals, and we have to have spares because we damaged them. And they're this sort of thick. You know, so this was an engineering marvel in itself. And the way that they make them is they were putting these crystals from a very small seed. And remember, they get this big, and they have to grow them in about a month or something now to make it viable. They were spinning, actually they weren't at the time, they were just in a liquid bath, and they're growing the crystal. They had to model this actually with 3D codes, so they had to model the flow around that to figure out how to get them to grow rapidly and uniformly. And that was a project which went on, must be 10 years ago, probably. And so now, again, that's another piece of technology which just didn't exist at the time that the project started.
You kind of anticipated my second question, actually. It is related to the lady's question about how beneficial is this research to general public. How about the side products of your research, like the technique to grow KDP crystals, that size, flawless, 192 of them, and how much of that gets disseminated in bits and pieces that isn't really your mission critical technology but could be applied elsewhere?
There's actually quite a bit. I wanted to get a list together for this meeting actually, but there, you know, there's the crystal growth thing is largely for those crystals. I'm not sure that's been employed anywhere else. The cleanliness on the glass, so that the glass, regular glass, is going to break very easily. The cleanliness on the glass and how you treat the surfaces. The intrinsic damage threshold is extremely high. It's still another order of magnitude or more away from where we are right now. That enables a number of, or can enable a number of advances in other technologies where you want very high fluences on glass, which is to do with, you know, directed energy and those sorts of things. There's also the beam itself, so that's for shooting down missiles and stuff like that. The beam itself is incredibly uniform, and that came out of something called deformable mirrors. What deformable mirrors are, they are put at the ends of, actually the end of those huge laser bays that we have, and they have small actuators on them. And you can diagnose how wiggly the wavefronts are as they come in, real time. And you can adjust the mirror to take those out. And this came out originally of something called GuideStar, which was actually looking up into the atmosphere, firing a laser up there, getting sodium atoms to fluoresce, and looking at them, and it should be a point source, a very small source. And it was for astrophysical purposes. So what they have now on a lot of telescopes is deformable mirrors. And you can imagine other applications for not necessarily looking out there, but looking elsewhere, where they have these sorts of technologies that can clean up what the atmosphere does to all of that light, so you can get very, very good pictures. So that's how we get phenomenal pictures of the universe from down on Earth right now.
Again, too impressive for words.
Thank you. There are multiple other applications as well.
Well, we're going to hold any other questions until after the last bit of housekeeping. If the speakers could come up here for a minute. We have a little present for all three of them. So if we could just stand along here. So we have a signed copy and framed of the announcement of your talk, one for each.
Thank you very much.
So thank you very much. Okay.